In this lesson, we're going to look at guidelines for finding absolute extrema for a function over a closed interval. Now, before we look at these guidelines, let's consider the graph of the function that we have drawn down here. Notice that this function has an absolute maximum occurring when x is equal to 4, and the absolute maximum, that would be about 16 or so on the y-axis. Now notice the absolute maximum occurs at the end point, where x is equal to 4, the right-hand endpoint for this function. Also notice that the absolute minimum occurs when x is equal to 1, and that is where the derivative does not exist for this function. Notice that that point right there is a cusp in the graph of the function. So that means that the derivative is not going to exist. So what we have here then is we have the absolute maximum occurring at an endpoint, the absolute minimum occurring where the derivative does not exist. Now, if we had smoothed out the graph a bit, like right here, well, then our absolute minimum would have occurred where the derivative is equal to 0. Notice that if I had smoothed it out a bit here, our tangent line to the graph would have been horizontal. The function, if it's smoothed out, the function will have a tangent line then, and it would be horizontal, and so the derivative would equal 0 now when x is equal to 1. So then the function would have had an absolute minimum where the derivative is equal to 0. Now consider this point over here. Over here we have a relative maximum. Well, notice that if we had pushed the graph up a little bit like this, and then brought it back down, well, now we would have had an absolute maximum when x is equal to -1, and the absolute maximum would have occurred where the derivative is equal to 0. Notice that we would have a horizontal tangent line there, and that means the derivative would equal 0 at -1. Remember, the slope of a horizontal line is 0. So the moral of the story here is that when you're looking for absolute extrema for a function over a closed interval, the absolute extrema are either going to occur at the endpoints, like 4 here for this function, or where the derivative is 0, or where the derivative does not exist. And so that gives us the guidelines that we have up here that we can follow to find absolute extrema. So the first thing we want to do when looking for absolute extrema on a closed interval, it's important that it's a closed interval, the first thing we want to do is find all the critical numbers. That is, we want to find where the derivative is 0 or does not exist, and we list out those numbers. Then we throw the endpoints into this list. Then we evaluate f of the endpoints, and we evaluate the function at all the critical numbers. Now we're guaranteed that the absolute maximum and absolute minimum for the function will be one of these numbers. So then all we have to do is pick out the largest and smallest values, and those will be our absolute maximum and absolute minimum. So then this process tells us where the absolute extrema occur and what their values are. Now let's take a look at a few examples. So let's find the extrema for this function over the interval from -1 to 2. So we want to find where our first step is to find where the derivative is 0 or does not exist. So we look at f prime of x. That's equal to differentiating this. We're going to get and now that can be factored as like that. Now we have to find where this is equal to 0 or does not exist. Well, obviously that's going to be at x equaling, well, let's see. This is equal to 0. 12x squared equals 0 when x is 0. And x minus 1 is equal to 0 when x equals 1. And since this is a polynomial, we don't have to worry about it not existing anywhere. It actually exists everywhere. The derivative exists everywhere. We're not dividing by anything, so we don't have to worry about the denominator equaling 0. So here are all of our critical numbers. Now we just have to throw our endpoints into the list. So then we have the points -1, 2, 0, and 1. We just throw our endpoints into the list. And now we just have to test the function at all of these points. So now we test f of -1. And if we put -1 in here for x, we get back 7. You can check that out. Put -1 in here for x, you will get back 7. F of 2. If we put 2 in here for x, you can check that we will get back 16. So there's our endpoints, and then our critical numbers. Well, if we put 0 in here, obviously we get back 0. And if we put in f of 1, we're going to get back 3 minus 4. That's going to be -1. So we see right here, this is our absolute maximum. And right here is our minimum. And there you go. We found our absolute maximum to be 16. And that occurs when x is 2. And our absolute minimum is -1. And that occurs when x equals 1. And graphically, we can verify what we've just found here. Here's the graph of what the function looks like. And notice that at 2, when x is 2, well, yeah, that does look like an absolute maximum over the interval from -1 to 2. This is clearly where the function has its largest value. And at 1, right here's 1 on the x-axis, our function value is, that's -1 right there on the y-axis. And yes, that does look like that's where we have an absolute minimum. The function values are all larger than -1 over the interval from -1 to 2. And there you go. So we found our absolute minimum and maximum by first locating our critical numbers, then throwing our endpoints into that list, and then testing the function at all of those points. Let's take a look at another example. Now here we want to find the extrema for f of x equals x squared minus 1 to the 2/3 power over the closed interval from -2 to 3. Now if you'd like to try this one on your own, you can pause the video here. So let's go over the answer. So the first thing we want to do is find all the critical numbers for this function. So we want to find where the derivative is equal to 0 or dne. So let's take the derivative of this function. So f prime, that's going to equal 2/3 like that. Notice we subtract 1 from 2/3 gives us -1/3, and that we will write as like this. Now, this will equal 0 when the numerator is equal to 0, as long as the denominator doesn't equal 0 at the same spot, and it will not in this case. So we'll set 4x equal to 0, and that tells us that x is equal to 0. So that's where our derivative is equal to 0. Now the derivative does not exist when the denominator is equal to 0. Now this will equal 0 when x squared minus 1 is equal to 0. Right? Because we don't need to worry about the 3. We can throw that out. And we can raise both sides to the third power. And then we just get x squared minus 1 is equal to 0. So this is equal to 0 when what's inside the parentheses here is equal to 0. Because 0 to the 1/3 power is 0. And of course this term right here factors as x plus 1 times x minus 1 equaling 0, and this is equal to 0 when x equals plus 1 or minus 1, plus or minus 1. And there we go. That's where our derivative does not exist. Now we have our list, and we have to throw the endpoints in. So our list so far is 0, 1, -1, and then we need to throw the endpoints in, -2 and 3. Now we just need to test our function at these points. So now we'll test f of 0. Well, let's see. If I put 0 in here for x, we get back -1 to the 2/3. That's going to be +1. You can check that out on your calculator or just reason it out. F of 1, well, that's going to be 0, right? Because 1 squared minus 1 is 0 to the 2/3. That is 0. F of -1 is also going to be 0 if we put -1 in here for x. -1 squared minus 1, that's 0. F of -2, well, if we put -2 in here, that's going to be 4 minus 1. That's going to be 3 to the 2/3 power. Well, we have to evaluate that on our calculator. That's going to be approximately 2.08. And then if we evaluate f of 3, we are going to get 8 to the 2/3 power. Well, remember that's equal to 8 to the 1/3 squared, and that is 4. 8 to the 1/3 power is 2, squared is 4. Alright, so here's all of our information. We just have to pick out the largest and smallest values. So we have that. We see that our function has a maximum of 4 when x is equal to 3. And we have actually have 2 minimum values here. Or we have one minimum value of 0 occurring at 2 different locations. So we have a minimum of 0 occurring at -1 and +1. And there you go. We've identified our minimum for the function to be 0 over this interval, and that occurs at -1 and 1. And our maximum is 4, and that occurs when x is equal to 3 at one of the endpoints. And graphically, what is happening here, if we look at the graph of this function up here, it looks like this. So let's verify what we've found graphically. So here's what the graph of this function looks like. You notice that we have our minimum value of 0, that's 0 right there on the y-axis, occurring at -1 and 1. And notice these are critical numbers where the derivative does not exist. The derivative does not exist at -1 and at +1 because of the cusp. We also have a maximum right here of 4, and that is occurring when x is equal to 3. And so graphically this verifies what we have found. Now let's take a look at this example. And you can try this one on your own as well if you'd like. So let's find all the extrema for this function over the closed interval from -1 to 3. Alright, so the first thing we want to do, find all of our critical numbers. So we have to take the derivative of this function. So that's going to be alright, and let's simplify that a bit. These 3's of course cancel, and we get and there we go. Now we have to set that equal to 0 and find where it does not exist. So f prime of x, first of all let's find where it's equal to 0, so we need to set this equal to 0 and solve for x. Alright, so that implies that and let's multiply the x to the 1/3 over to the other side, divide this 2 over to this side, and we're going to get alright, so we have that x to the 1/3 equals 1, and that implies that x is equal to 1. So that's where our derivative is equal to 0. And of course if we look back at that, well yeah, we could have seen that if we looked at this a little more carefully. Notice that 2 minus 2 divided by 1, well, that's going to be 0. Now we need to find where the derivative does not exist. Well, this does not exist. The only time this does not exist is when the denominator here is equal to 0, right? That's the only time this is not going to exist. So f prime of x does not exist when x to the 1/3 is equal to 0, and of course that implies that by cubing both sides, that implies that x is equal to 0. So here's our another critical number. So now let's create our list. So our list so far is 1, 0. There are the critical numbers, and now let's throw in the endpoints, -1 and 3. And now we just have to test all of these. So let's start out with f of 1. So if we put 1 in here, we're going to get 2 minus 3 times 1 to the 2/3. And well, that's just 1, so we're going to get 2 minus 3. And of course that is -1. f of 0, well, that's going to be 0. If I put 0 in here for x, 0 minus 0, 0. f of -1, let's see, if we put -1 in here, we're going to get -2. -1 to the 2/3, that's going to be +1, right? -1 to the 2/3, that's -1 to the 1/3 squared. -1 to the 1/3, the cube root of -1 is -1 squared, so that's 1. All right, so this is going to be -3. So -2 minus 3, that is -5. And then f of 3, that's going to be 6 minus 3 times 3 to the 2/3 power. And well, we have to evaluate that on our calculator. negative 0.2403, rounding to 4 decimal places. Right, just check that out on your calculator. That one you have to use your calculator for, and that's what you get. So okay, now we just have to pick out our absolute minimum and maximum. Well, we see that right here is going to be our minimum. So f of x has an absolute minimum of -5, occurring when x is -1. And it has an absolute maximum of 0, occurring when x is equal to 0. So this is our max, and this is our minimum. And you could just write out that f of x has a maximum of 0 when x is equal to 0, and f of x has a minimum of -5 when x is equal to -1. And there you go. We found our absolute minimum and absolute maximum and where they occur. All right, so that concludes this discussion. Oh, and before we leave, let's verify what we found here graphically. So here's what the graph of this function looks like. So right here is its graph, and we did find that we had a minimum of -5 occurring when x equals -1, so that looks correct. And we had a maximum of 0, that's 0 on the y-axis, occurring when x is equal to 0. And that looks correct right there. So there's our absolute minimum, and here is our absolute maximum for this function over the interval from -1 to 3.